Hello, good people of AP Calculus. We are going to begin the Odyssey that is differential equations today. I'm going to begin with a little demonstration to explain what a differential equation is. Imagine that you have a cup and that the cup is filled with water. So you can tell it's water because it's blue. And you punch a hole in the bottom of the cup. Well, no surprise that when you do that, water is going to start pouring out of the cup. And here's what we're interested in. We're interested in the relationship between the volume of the cup and the rate at which the volume changes. Okay, so of course, when I use these derivative symbols, that means that we are talking about a rate. So what's going to happen? As the volume goes down, we know the volume is going to go down because there's a hole in the cup. What's going to happen to the rate? Is the rate going to stay constant, like the water will just come out at the same rate all the time? Or is the rate going to speed up as the water goes down? Is it going to go out faster and faster and faster? Or is the rate going to decrease, like the water is going to come out slower and slower and slower? So think about which one you want it to be. Is it going to be faster, slower, or constant? And I actually just happen to have a container of water right here. And I have a cup, and this cup has a hole in it. So let's do a little experiment. Oh, I should probably put my finger over that hole, huh? Let's pour the water in. And here we go. When I take my finger off the end here, we are going to watch the water fall into the container. Now, I'm going to level with you. It's kind of going to sound like someone's peeing. So, teenage boys in the classroom, go ahead and laugh. But while you're doing that, I want you to be paying attention to what happens to the rate. Does the rate get faster? Does it get slower? Or is it constant? Here we go. Okay, so you can see here at the end, it's just like it ultimately at the end, it's just these like a few slow drops. So as the volume was going down, so was the rate. All right, so what does this mean that as the volume decreases, the rate also decreases? Well, it tells us something about the graph. We know that if we started with a volume up here and sometime later we had a volume of 0, then the rate must start being steep and get less steep as we go along. So the graph is going to look something like that. So you want to think about what kind of function would this be? It's not linear because it's curvy. Well, we're going to find out. All right. So here's the meat of what we are doing today. It turns out that when you have a volume that's diminishing, the rate at which the volume changes as time goes by is proportional to. K is a proportional constant. This is a constant. It's not changing. It is proportional to the square root of the volume. Why? I actually don't know. Ask your physics teacher. Now, our goal is to solve for V, because that'll tell us what kind of equation we have right here. And unfortunately, we can't just anti-derive. There's a good reason for that. This has never happened before in calculus, but it's happening today. The thing that is on the other side of the equation, right here, the V, is the output. Right? V is the output. Time is the input. Every equation we've done all year so far that had a derivative in it, this was an x. Well, today, this is a y. And the way that you solve when you run into this sort of situation is what we call a differential equation. So step number one is going to be that you need to bring the v's together. So I'm going to take both sides of this equation, and I am going to divide by roots of v. So we're going to get, that shouldn't be a t, that should be a dv in the numerator, divided by the square root of v. Once again, this divided over here is equal to, on the other side, our proportional constant, which is just a number, multiplied by, you're going to multiply the dt over here. Okay, so that's step one. See how the v's are over here and the t's are over here. Now the next step, I want to clean this up just a little bit. I'm going to move the v into the numerator, and it would have an exponent of negative 1/2. Man, if these two expressions had an integral symbol, that would look like an integral. That's actually our next step. You're going to integrate both sides. I'll start with this side. Power gets kicked up by 1, so the power is now going to be 1/2. Multiplied by, we need a constant right here. 1/2 times what would give us a coefficient of 1? The answer is 2. On the other side, we are going to kick the power up by 1. Since this is a number, imagine what you would do if this was a 2. Were this a 2, you would say 2t. But it's a k, so we're going to say kt plus meow, the cat. Now, you could put a cat on both sides, but I found it's easier to just pick one side, always the right side, and put it there. We can talk more about why later, but for today, let's just leave it at, you're always going to put the constant over here on this side. Okay. Next step, we now want to solve for v. So we're going to take both sides. We're going to divide by 2. We get that the volume of the container to the 1/2 power is equal to the constant times t plus c divided by 2. And then our last step is going to be to square both sides so that v is by itself. And it turns out that v is equal to a quadratic equation. This is called a family of functions because it has a constant in it. It's got the c, and it's also got the k. So this is the quadratic or a quadratic family. If I gave you the volume at specific times, you could solve to figure out what k and c are. But I'd like to note that this actually makes a lot of sense, because if you look back here, can you guys see that this right here is in fact a section of a parabola? So f of x is quadratic. Cool. Now that's kind of a high-powered example. Let's go with two a little more straightforward ones. This is a nice extension of that problem, but for the video, I'm going to say let's skip that part. And let's move on down here. These are the steps for solving a differential equation. See this right here? Just let that sit off to the side and scare you for a while. For now, let's look here. First thing I want you to notice is that we know this is going to be a differential equation because it has the output. It has the y in it. So the method that I'm about to teach you, seeing that there's a y right there tells you that this is what you're going to do. Step 1, rewrite the equation so that dy dx equals some factor on the other side. Oh, already done for you. Thank you, Mr. Klein. Step 2, you want to rewrite this with the y's and the dy's on the left, and then the x's and the dx's on the right. So I'm going to take this y here. I am going to multiply it so that I get y on this side along with the dy. And then on the other side, I'm also going to multiply the dx so that we get negative 6x is multiplied by dx. So step 1 done. Step 2 done. Step 3, take the indefinite integral of both sides of the equation. So integral integral. On the left side, we get 1/2 of y squared. On the right side, we get negative 3x squared plus. Okay. Now, next thing, notice that I gave you a specific condition right here. I said that it's going to go through the point 0, -5. This would be a good time to mention this guy. This is called a slope field. This is giving you the slopes of this equation at billions and billions of different points. I'm just going to mention slope fields today. And then in a couple of classes, we'll get more deeply into them. But it might be helpful to note that we know that our curve has to go through that point, which means that at x equals 0, it has a slope of 0. And over here, it has a positive slope. And those slopes seem to be getting steeper. So the curve's going to look something like that. This is guesswork. It's not exact. And then on the other side, it's going to look something like this. There will be a couple discontinuities on the y-axis. We'll talk about y another time. Don't worry about that for now. So this looks like half of an ellipse, and we want the specific equation, which means that we need to plug in the 0, -5. Now, what I would recommend is that we not do it just yet. Right now, I'm going to ask you to multiply by 2 and multiply by 2 just because it's going to clean the equation up a little bit. And over here, we're going to get y squared is equal to 2 multiplies this. So we get negative 6x squared. 2 multiplies this, which gives us 2c. Now, a hot tip. See that 2c right there? C was a constant, a number. We don't know what it is, but some number. And if this is a number, that's supposed to be a little number symbol. Isn't this also a number? The answer to the question is yes, it is. So you're going to see me do this. I'm going to, rather than writing 2c, I'm just going to write plus c1, reflecting that we have a new constant right here. All right, now would be a good time to take this point, bring it around here, and plug it in. We could have plugged it in up here and it would have been okay. Anytime after you anti-derive, it's legal to plug this point in. I think this is the best time. All right, so over to the side here, -5, the quantity squared, is equal to -6 times 0 squared plus c1, which means that c1 is equal to 25. So let's bring that back. We get that y squared is -6x squared plus 25. And to get our equation, we're going to take the square root. Recall that when you square root, you get 2 answers. You get a positive and a negative. We need to choose one. Here's what I would suggest. Look at the point we were given and the graph we ended up with. See how all the y values are negative? That means that you're going to choose the negative one. So our final answer is going to be the quantity y is equal to negative square root of -6x squared plus 25. Okay, good people of calculus, let's do one more. Flip to the next page. If you're feeling up to it, maybe you want to try this one without me and then check your work. So if that's what you'd like to do, go ahead and pause the function, or the function, pause the video. If you would rather just watch me do it, I'm going to do it right now. Step number 1 is to get the rate by itself. So I'm going to subtract that expression and get that dy divided by dx is equal to negative 2xy squared. Step 2 is to isolate y and x. So divide both sides by y squared. Over here, you will get 1 over y squared dy, or just dy over y squared, doesn't matter, is equal to negative 2x gets multiplied by the dx. Next up is we're going to anti-derive, and that'll be easier if we rewrite this as y to the negative 2. Okay, integral. This side, we're going to get y to the negative 1. Negative 1 times something would give us 1, so we need a negative right there. On the other side, negative x squared plus meow. Now, we have a point. That point is 1 comma a half to plug in. If I plugged 1 comma a half in down here, I'd get here's 1, here's a half. We can see that the slopes are negative right there. It's kind of hard to see what's going on in this one, but what is going to happen is it's going to level off, and then we're going to get some symmetry like that. And I know it's hard to see, but this thing is actually going to level off this way and this way. For those of you taking statistics, it's going to look kind of like a normal curve. To get the actual equation, hey, let me emphasize one more time. You don't have to know how to do this yet. I'm just showing you. Negative 1 over 1 is equal to negative x squared plus c. And then I'm going to take both sides and I'm going to multiply by negative 1, which gives us y, or 1 over y. On the other side, when we distribute, we get x squared. Here, rather than writing minus c, because I don't like negatives, I'm just going to say plus a new constant. And this looks like a really good place to plug our point in. So let's bring that point down here. 1 over 1/2 is equal to 1 squared plus c1. So this is 2. Therefore, c1 is 1. So we're almost done. We have 1 over y is y squared plus 1. Therefore, if you think of this as two fractions, you can just do a little flippy doodle. And you're going to end up with the equation is y over 1 is equal to 1 over x squared plus 1. And that is the game, ladies and gentlemen. You now know everything that you need in order to do both assignments 1 and 2 for the unit.